G'day! In this video, we're going to start to look at the motion of charged particles in two dimensions. We're covering syllabus point 6.1.2. Our focus is on electromagnetism and describing the motion of particles when they interact with electric and magnetic fields. Our focus is still on electric fields. We're going to be modeling the trajectories of charged particles in electric fields and compare them with the trajectories of projectiles in a gravitational field. So our clear learning intention today is to apply mechanics equations, especially those that we looked at in Module 5 and projectile motion, to the motion of charged particles in two dimensions. So what I want to show you first are two diagrams which describe the motion of two different objects when they're placed in two different fields. In part A, we have a charged particle that is moving through an electric field. And we see here that this positively charged particle doesn't just move in its direction of initial velocity, but also starts to accelerate and move towards the path of the electric field. The same thing happens for a regular object being moved through a gravitational field. In other words, how projectiles move on Earth. So today we're going to be showing some similarities and parallels which can be drawn when analyzing the motion of charged particles in an electric field and seeing how we can treat them quite similarly to how we treat objects that move through gravitational fields as projectiles. So here I've just pulled together a couple of key diagrams and tables which summarize, I think, all of the things that we need to consider quite eloquently. First off, what I want to show you here is that if an object is moving through an electric field with an initial velocity, u, that should be quite familiar, we can break up that velocity into two components that are perpendicular to each other. So in the same way that we had uy and ux and vy and vx in our projectile motion calculations, here we have u parallel and u perpendicular, where u parallel is one perpendicular component which is parallel to the electric field. Note here that this u parallel is actually anti-parallel to the electric field, so we can have u moving against the field, just like we do when we have projectiles moving against the gravitational field in the y-axis. We also have u perpendicular, which is perpendicular to the electric field. This would be akin to ux in our projectile motion work. As always, it's really important to remind ourselves that positive and negative charges will move either with or against the electric field, and this is something that's quite different to projectiles when we're looking at gravitational fields, because all objects move with the gravitational field. We don't have any that move against it, but it is something that you're going to have to be conscious of and consider when solving problems and completing calculations. In projectile motions, our A parallel to the field or our y-axis, our acceleration in the y direction, was always just g, the acceleration due to gravity. However, this formula here, A parallel is equal to EQ on m, is going to be a lot more useful to you because this is going to be reflective of not just the electric field that the particle is in, but also the charge and mass of the particle, all factors which are going to influence its acceleration. Now, we did look at this formula, maybe just not in this form, in the previous video where we combined F equals ma and F is equal to EQ. So when we combine these two, we have ma is equal to EQ, which means that A is equal to EQ on m. And what this means is the acceleration of the particle depends on the electric field that it's in, the charge of the charged particle, as well as its mass, all being factors to dictate the acceleration of the particle. However, something that isn't going to change in this scenario is that A perpendicular is equal to 0. So in the same way that AX is equal to 0, or it was at least assumed to be because we weren't considering any form of air resistance, we make the same assumption here, that as the particle moves through the electric field, the perpendicular component of motion is going to have no acceleration. And thus that's going to be reflected in some of our kinematic equations. So what you should see here is that all of the assumptions and equations that we've used for the x component of projectile motion is matching up with things that are perpendicular to the electric field, as well as things that are working in our y component, which are parallel to the gravitational field. Our formula are quite similar to how things behave for charged particles, which are parallel to an electric field. Note 2, while the table doesn't include it, there is most definitely the possibility to be using the v squared equals u squared plus 2as formula as well. All you would need to do is just change up your notation and your values for acceleration. So while we'll dig a lot deeper in class, let's just do a really short practice question to demonstrate how there is this overlap between what we've learnt in Module 4 and the very beginnings of Module 6, and how that's related to and combines with concepts that we've learnt about, particularly in Module 5. So in this question, we have a scenario that describes an electron gun that's been placed near a set of parallel charge plates. They are 2.5 centimeters apart and have a potential difference of 12 volts. The electron gun emits an electron that is traveling at 3 times 10 to the 7 meters per second, and the electron enters the uniform electric field equidistant from each plate, and it's also traveling perpendicular to the field. We're being asked to calculate the time taken for the electron to collide with the positive plate. What I'm going to do first is draw a diagram of this scenario in all of its parts from a few different angles, including lots and lots of data from the question, so that we can get a really good visual representation of what's being shown here. So in this diagram, I first set up two charge plates that were parallel to each other, generating an electric field. I then put in the data for that electric field that the plates were 2.5 centimeters apart, converted that to meters though, and that the potential difference was equal to 12 volt. I've also drawn in that the electron was entering the field, but I didn't feel like there was really enough room to get all of the information in that I needed. So I kind of just blew up that section and did a little bit of a redraw. Here I drew in the vector for u perpendicular, which is equal to 3.0 times 10 to the 7 meters per second. So note that this direction might be parallel to the plates, but is perpendicular to the electric field. Thus why we've used this perpendicular notation here. The u, the initial velocity in the parallel component, so the velocity which is parallel to the electric field, here is equal to 0. I've then drawn a little bit of a trajectory to show where I expect the electron to go, and while it's still moving from left to right in the diagram, it is progressively moving further and further and further towards the positive plate, and that's what's being shown here. As we have been told that the particle enters the electric field equidistant from each plate, what that means is that there is 1.25 centimeters below the electron and 1.25 centimeters above the electron to get to either plate that's below and above. Here, what that means is the electron is going to move 1.25 centimeters to get to that positive plate. And so with all of this data, what we should be able to do is now calculate for the time taken for that electron to collide with that positive plate. So what we'll do first is identify some key equations. First, let's make sure that we know what our acceleration parallel to the electric field is going to be, and that's EQ on M. Now, the electric field strength is not something that we've been given in the question, but it is something that we can calculate for with some other values that we have, because we know that the electric field strength is equal to the potential difference divided by the distance between the plates. And so once we have that acceleration, we can use that and some of the other kinematic data that we have to calculate for the time to hit the positive plate. And that's going to be done using our S equals ut plus half at square formula. Let's start by calculating for acceleration first. So now that we have our acceleration here, we are going to be able to calculate for time. But before I do that, I do want to note that I didn't substitute in a negative value for the charge here. I did just take every value as an absolute value. In other words, all of the values were substituted in as positive. This gave me the magnitude of the acceleration. And this little shortcut can be helpful because at times the positives and negatives in these styles of calculations can be a little bit tricky to wrap your head around. But conceptually, deciding what direction the charged particle needs to move towards can be quite a straightforward process. So generally speaking, if you do sort of use absolute values to calculate the magnitude of a vector, and then at the end make sure that you're writing down the correct direction based on, a conceptual diagram, you're probably fine to just do that rather than try and manage all of those negative numbers as you go. Now let's have a look at using our kinematic equations to calculate for time. So what we see here is that the electron will reach the positive plate in a fraction of a second. It's going to take 1.7 times 10 to the negative 8 seconds to get there. Thank you very much, everyone. In the next video, we're going to be looking at applying magnetic fields instead of electric fields to charged particles and looking at how they interact. But until the next time, have a good one.